Hi, Bobcats. Welcome to Properties of Integer Exponents, Part 2. Let's dive right in. Here we go. Division properties of exponents. Write as a fraction. So when we look at this very first problem, let me get you back. There we go. Already messing up, Miss Keller. Okay. So when we look at this very first problem, we want to write as a fraction. So we see 6 to the 5th divided by 6 to the 3rd. We write it as the fraction of 6 to the 5th over, that bar means division. We say over 6 to the 3rd. Think about it in the terms of 6 multiplied 5 times. 6 times 6 times 6 times 6 times 6. And we've kind of talked about this premise in our last video in part 1, but now we're looking at the quotient of powers property. And then we look at 6 to the 3rd. 6 times 6 times 6. 6 multiplied 3 times. The quotient of powers property states that when dividing two exponential expressions with the same base, subtract the exponents. When I have the same base, I can subtract the exponent values. So when I look here, I see a correlation. I see that 6 over 6 is 1, 6 over 6 is 1, and 6 over 6 is 1. So these can easily cancel out to give me 6 times 6, or 6 to the 2nd power. Remember, 6 over 6 is just 1. So when I look here, bam, 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 all gone, canceled out, and I'm left with 6 times 6, which is what we see here. Or, in a more simplified form, 6 to the 2nd power. Quotient of powers property. So let's practice a little bit. You see the property rule above there. When we have bases that are the same, we're going to subtract the exponents. So we notice here in the first one, we have 3 to the 7th over 3 to the 3rd. I write it as 3 as my base. 7, I show that work, so I know that I'm subtracting minus 3, which equals 3 to the 4th. Here I have the same basis as 8, so 8 stays the same. 7 minus 2, which is 8 to the 5th. Not 85, 8 to the 5th. Same basis, 7 and 7, so I have 7, 5 minus 4, which is 7 to the 1st, or you might see it as 7. And same basis, 5, I have 5, 9 minus 5, which is going to equal 5 to the 4th. Okay. Remember, at any time, Bobcats, you can pause the video and take notes. I highly suggest that you have your focus notes out with your Math Interactive notebook, and that you're pausing this video to write the division properties of integer properties of division of exponents, so you have them in your notes to refer back to with your playlist that you'll be working on this week. All right, let's consider the following problem. Let's think a little bit about this problem. It's going to lead into our next property here. What would this expression be equivalent to? Hint, let's use the product rule. So the product rule told me that I could take 3 to the 2nd times 3 to the 0 power, and I have the same basis. So if I have the same base, I can add the exponents. I get 3 to the 2nd power, and 3 to the 2nd power is just 3 times 3, which is just 9. Okay, remember, it's not 3 to the 2nd power, it's not 6, it's 9. So if I know that this is 9, how can I then use the following? If I'm just kind of given a symbol, right? Trying to prove what 0 is and why. What must 3 to the 0 be to keep these expressions equivalent? Remember, I want these expressions to be equivalent. What we just did up here, I want to be equivalent to what we're going to do down here. So let Elmo equal 3 to the 0 power. If Elmo equals 3 to the 0 power, and I have this expression, 3 to the 2nd times Elmo equals 3 to the 2nd, well, think to yourself, well, how can Elmo give me this answer? But Elmo is 0 power. What must Elmo be in order for me to get 3 to the 2nd power as my answer? I'm going to give you a few seconds to think about that. 3 to the 2nd power times what could give me 3 to the 2nd power? Hopefully you said 1. So Elmo equals 1. 3 to the 0 power is 1. Anything to the 0 power is 1. So let's take a look at this a little bit more closely. Let's use the pattern to evaluate 3 to the 0 power. We see here the exponential form of 3 to the 4th is 81, 3 to the 3rd is 27. We see this as we divide, and it gets smaller and smaller, right? If we have 9 divided by 3, we then go down to 3 to the 0 power, and 3 divided by 3 is 1. Look at your powers and how they decrease as well. The powers are decreasing, and as they decrease, we're dividing by 3 each time. Use the quotient of power rule to determine the value of 3 to the 0. 3 to the 3rd divided by 3 to the 3rd is essentially saying, and using that quotient rule, that quotient power rule of 3 to the 3rd minus 3 is 3 to the 0 power. So again, here's multiple rules that we've talked about. We're using them again as we look at different laws of exponents. And if I have 3 to the 3rd over 3 to the 3rd, it's essentially saying 3 divided by 3, 3 divided by 3, 3 divided by 3, which is 1. There we go. So 3 to the 0 power is 1. Anything to the 0 power is 1. So let's evaluate each power. Negative 7 to the 0 power, 1. 43 to the 0 power, 1. 1 to the 0 power, 1. 0.5 to the 0 power, 1. Now, please don't get this confused with having a negative exponent. If I had 7 to the negative 6th, that is completely different, right? So that's not going to equal 1. That base can be negative as long as the power or the exponent is 0. So convince me. Well, if I have y is 2 times the parentheses of 7 to the 0 power equal to 2. Well, 7 to the 0 power is 1, and 2 times 1 is 2. So 2 equals 2. Okay? Think about that 0 exponent rule. A to the 0 power equals 1. If we're simplifying 15 to the 0 power, that's 1. B over C to the 0 power with those parentheses, it's still going to equal 1. Okay? So what is the meaning on a negative exponent? If we have 4 to the 3rd divided by 4 to the 5th equals 4 to the 3rd over 4 to the 5th. Remember, we're just taking this division problem now with these exponents and writing it in a fraction form. So let's expand that further off of what we kind of just talked about from our last previous slides. Now, I can see here that I have 4 to the 3rd. That's 4 times 4 times 4. 4 is multiplied 3 times. And I have 4 to the 5th, which is 4 times 4 times 4 times 4 times 4. 4 multiplied 5 times. Now, I'm showing you this because I want you to understand conceptually what that looks like when we're breaking that down and trying to get that negative exponent. Now, we're going to have much larger numbers, which means that you're not going to be able to do that with a power. If it was 4 to the 50th power over 4 to the 60th power, those are numbers that are huge. You're not going to write 4 60 times or 4 50 times, right? So think of this as just understanding the concept of why do we have, or what is the meaning of that negative exponent. So when I look here, these can easily cancel out like we've discussed before. So let me get, bam, 1, 1, 1. Now I'm left with 4 times 4, right? But this is 1, this is 1 up top. So these simplify to 1 over 1, 1 over 1, 1 over 1. 1 is left on top, and this is 4 times 4, which is 16, which gives me 1/16. So this essentially becomes 1 over 4 times 4, which gives me 1/16. So if we follow the quotient of power rules, 4 to the 3rd divided by 4 to the 5th equals 4, parentheses, 3 minus 5, which equals 4 to the negative 2nd. This right here is equivalent to what we just talked about over here. We're left with 4 to the negative 2nd. Therefore, we can't have a negative exponent, so we must follow the negative exponent rule and make sure that our exponent is positive. In order to do that, right, think about this, negative 4 times negative 4. Okay, yes, that's going to produce positive 16, but it's not going to be 16 over 1. You must take that reciprocal in order for that to happen. I want you to think with negative exponents, think about your powers of 10. Okay, Think about those powers of 10. If I said 10 to the first, you would say 10. If I said 10 to the second, you would say that's 10 times 10, which is 100. 10 to the third, 1,000. Now, if I said this was 10 to the negative first, would you tell me that it's 10? Does that make sense? Is that number getting larger? Is that number getting smaller? You notice here at 10 to the first, 10 to the second, 10 to the third, those numbers were increasing. Now, 10 to the negative first should not be 10. It's going to be 1/10. It is getting smaller, right? This is negative. 10 to the first, 10 to the negative first over 1, take that reciprocal, is 1 over 10 to the first, or 1/10. Okay, so as we look here in the table, I'm just going to go back and see if I can delete here. Okay, so we go back and we look at the table. It's giving me a hard time. Okay, we have -2, and then we have 1/16. -1, 1/4, 0, 1. Think of this as your input, your output, right? So if this is my rule, 4 to the x, 4 to the negative second, it's going to give me 1/16, 4 to the negative first, 1/4, 4 to the 0 power, anything to the 0 power is 1, 4 to the first is 4, 4 to the second is 16, and 4 to the third is 64. The same premise as what we were talking about with our powers of 10. Okay, so 4 to the negative second equals 1 over 4 to the second. Let's practice a little bit. You have your negative exponents rule right there to the side. As we go to practice, we can write each expression using positive exponents. 8 to the negative second is going to equal 1 over 8 to the second. You could simplify that to 1/64. Sometimes it'll ask you to leave it in the exponential form, so do pay attention to that. 2 to the negative fourth would be 1 over 2 to the fourth. 3 to the negative fifth would be 1 over 3 to the fifth. All right, so let's continue our work now looking at number 3 here, where it says p to the negative eighth over p to the third. Now, we have to think about our negative exponents rule in the fashion of making sure that we don't have that negative exponent. Remember, this is essentially saying you're multiplying that p so many times and p to the third so many times as well. So now we have to make sure we don't have a negative exponent, which means we're taking the reciprocal of just this term. That means that p to the negative eighth will be moving to the denominator value, and the numerator value will become 1. So this becomes 1 over, excuse how sloppy that is, 1 over p to the third times p to the eighth. Now, remembering our multiplication properties, integer properties of exponents, we know that when we have the same variable, we can simply add the exponent. So this becomes 1 over p to the 11th. Okay. Take a quick minute and just kind of refresh, pause the screen, snap a picture. If you didn't get all of those properties for division property, integer properties of exponents, make sure you have these in your focus notes. Reach out with question bobcats and have a great day.